Okay, good morning, everybody. So I again welcome Professor Amey Karkare for his session. Again, I would really urge you guys to be interactive and ask as many questions as you can. Amey, it's all. The stage is yours.
Okay. So good morning and thank you, Shubhajit. So in fact, my three sessions, they cover three different parts of compiler and runtime system. So yesterday we talked about type system, which comes somewhere here in the semantic analysis phase. Okay. And typically where you have typed languages, once semantic analysis is done, most of the time types are thrown away because backend assumes that your program is correct, type correct. Okay, so then today's session we'll talk about code generation in the morning. In particular, we'll have some extra emphasis on register allocation. And in the next session, I will be talking about garbage collection, which is more of a runtime stuff. So that way I'll be covering front end, back end, as well as runtime systems in this three sessions allotted to me. Now, Shubhaji, just one thing, because probably Professor Shrikant said he will have a session in the morning, but earlier he had asked me to swap the session. So please double check when will my session be and when will his session be. So I am ready anytime. Okay, so you can get that confirmed.
Yeah, I think the next session is Shrikant sir's. I think the afternoon session is yours.
Okay, fine. All right. So code generation. So once again, you may have done some compiler course and you may have created a project. And unfortunately, the way our semester system goes, when we reach the point where code generation is there, we are mostly covering theoretical things. Excuse me. But students get very less time to spend on code generation in their project. And I know some instructors like Shubhajit also, they have started covering code generation before other phases. Okay, but apart from that, suppose you are going to use a compiler, production compiler, professionally written and all. So what are you going to look for in a compiler as far as code generation is concerned? Okay, so here are a few of my thoughts, and you can also add on chat window. I'm continuously looking at that. So first and foremost important is you would like your output code to be correct. Okay, so if you are generating an executable, it should behave in the same way as you expect your program. I mean, you have written a program to square a number, the output code should also square a number. There are few issues like again floating point issues or maybe overflow, underflow, but barring that, it should not introduce its own behavior. Secondly, output code must be of high quality. Again, quality parameter here depends on what you are looking for. So it could be speed, it could be power consumption, it could be maybe you are talking about some kind of safety critical system. So it should take care of unexpected scenarios and so on. So quality, we are not defining it to be speed only. It can be many things depending on the application. And finally, you would like your code generator also to run efficiently. I mean, just because you want a high quality code should not mean that a small 5-line program, it takes 20 hours to compile. Okay, and I would say this is not unheard of, especially when you are looking for a compiler which also verifies your code. So a 20-line code might take a few hours to verify and give output. So what are some other issues in code generator? So anyone else who has any inputs? Okay, so these were kind of very high level requirements that we want, but when you are writing code generator, there are challenges. So Yashas is saying easy to maintain across many targets. No, in a way, when you're talking about code generator, you are typically thinking of a single target. Now, this target itself could be a virtual machine. Okay, so code generator does not know about many different targets. So that way, it cannot generate what do you say portable code. Okay, so then your targets have to be such that they are compatible with each other. But then you have these ideas of just-in-time compilation, where you kind of add another phase between compiler-generated code and when you start executing the code. So there is this phase you can call elaboration, or you can call during the execution itself. So in a way, it runs kind of hand in hand with your runtime system, which does compilation. Certain part of code are compiled specific to the given architecture, current architecture. But yes, you may want that the source code of code generator should be easy to port across multiple architectures. And this is what GCC does using what is called an op table, some kind of machine description files and so on. So in GCC, even a machine is described using a configuration file. So target architecture is described using machine description file. So that same compiler code kind of works for many different architectures. Okay. So now the code generator, we assume that input is some intermediate representation along with symbol table, and it has been validated. Target programs are absolute machine language, could be absolute machine language, which is very good if you, especially if you have if you have small programs, it will be very fast. But then it is also difficult to get it correct for large programs. So typically we generate what is called relocatable machine code, okay, which requires linker and loader. Some part of it I think is covered already. And many times you will also generate assembly code rather than relocatable machine code. Now with assembly code, assembler generates relocatable machine code, and then linker and loader take care of it. I think this was covered in one of the labs earlier. I was there for some time. Okay. The advantage of introducing assembly code is, yes, assembly code is not as readable as high level code, but it is not as unreadable as your binary code. So now the challenges with the code generation are you have to select instructions to generate. I mean, with complex architectures, you can have many different instructions which can give you the same output, but you would like your instructions to have certain properties like uniformity. So their structure should be similar. Okay, all this is important because once again, architectures, when they have these instructions, when they're executing it, the issues of caches, locality, all these come into picture. Okay, and similarly, debugging also becomes easier if you have instructions which are uniform. The instructions should be complete with respect to the source language, in the sense everything which is present in source language, you should be able to express it in terms of the instructions that are there. And finally, one of the important thing is speed as well as power consumption. So if there are multiple instructions, depending on the architecture, maybe if you are using a generating code for a supercomputer, you will not worry that much about power consumption. Supercomputers or large computers will anyway use a lot of power. On the other hand, if your code is supposed to run on a mobile device, you will worry less about instruction speed, you will worry more about power consumption. And another issue is register allocation. So many machines, either they have this restriction that you can do certain operations only on registers, or if that restriction is not there, even then any operation on register are going to be much faster than if they are done on memory. Okay, so which means you want to use or prefer instructions which have register operands. We would like to store values which are used very often, just like some counters in registers. Temporaries which are created and destroyed, they need not get memory locations because you will unnecessarily be loading and storing the values. So typically you would like temporary locations also to go into registers. And even with register allocation, there are certain constraints. So for example, on Intel machines, you know that if you have X bit numbers, then their 2x bit numbers will produce output of multiplication, which could be twice the X. Okay. So some architecture have what is called odd even register pair, where the result of certain operation will go into certain part will go into odd number register and certain part will go into the next even number register. So you during register allocation, you have to make sure that you are generating code taking care of this odd even property. Okay, so all these are issues. In our discussion today, we are not going to worry about even or register pairs. And another interesting or important aspect is evaluation order. Okay, now when we say evaluation order, compilers, in fact today almost all kind of compilers, they will rewrite your binary or reorder the instructions in the binary. Instruction need not be in one-to-one correspondence in order as your source code. And can you guess what are the reasons for this reordering? Without changing the meaning of the program. That is important. So without changing the semantics, without changing the meaning, they still try to reorder instruction. Compilers try to do that. So any reason why a compiler would like to do that? Performance, why? Reduce stalls. Very good. So yes. So one of the major reason is nowadays most architectures will be pipeline architecture, or if you also have parallel architecture in other sense. Okay, you might want to reorder instructions to reduce dependencies and in general to reduce stalls, improve branch predictions. They might do loop enrolling. I think yes. So Ashutosh has given quite a few answers, and Yashas has given 1 or 2 answers. Compilers, typical compilers do not worry about caches as such, but yes, they also want to put instructions together, use and so basically definition and use together. And we will see some very trivial examples, not very complex examples here. Complex examples you might have seen in architecture course, or you will see. Okay. So now code generation correctness is not a very difficult thing, as long as you can generate an intermediate representation. I think generating another kind of representation is not a very big deal. So you already know probably that 3 address code like instructions are very easy, and you can simply do one-to-one translation to machine code. Okay, as long as your machine code instruction set is sufficiently rich, it will be easy to translate everything from 3 address code to machine code. So correctness is not that big an issue, but efficiency is an issue. So consider this very simple code: A equal to B plus C, D equal to A plus E. Assuming we have this instruction set where the second argument is a register, and it is also the result of the operation. So you move B to A R0, and then you add C to it. So it becomes B plus C in R0, and then we are moving R0 to A. So this part of code is computing A equal to B plus C. And assuming once again we have a very simple technique for code generation, which goes step by step into every instruction and generate corresponding code. So you can see very easily we can generate code for A plus E. We are moving A into R0, we are adding E to it, and then finally we are moving R0 to D. So this corresponds to second instruction. Okay. Now everything is correct, everything is perfect. If you look at them standalone, you can't do much, you cannot save anything. But when we put these 2 instructions together, you realize that there is an unnecessary instruction here. You have moved R0 to A and you have moved A to R0. So as such, you cannot find any redundancy in individual statement, but when we look at it together, then there is a redundancy. We are unnecessarily storing value into A and then we are loading it back. So any decent compiler will be able to eliminate the second instruction. Similarly, another example, suppose you have A equal to A plus 1. If efficiency is not an issue, probably you will just go through the rituals again like we did for earlier. You move A into R0, you add 1 to it, and you move R0 back to A. On the other hand, suppose your instruction set is quite complex and it has an increment instruction which works directly on memory. Okay, so you might be better off running a single instruction increment A. So generally such an instructions are available for register, and maybe they will be faster than this. So even if you have to do all this, it might be better to run an increment R0 instruction than adding 1 to it. Okay, so these are the kind of issues. You have multiple choices. You have to select the one which is best, and that is what makes code generation complex. And as I said, most often the choice which will work better will involve register, and the number of registers is limited. So you now have this trade-off whether to use register and somehow take care of the contention that multiple instructions want to use it, or use memory addresses and so on. So you have to find some way of balancing the trade-off. Okay. So any queries? So our focus today will be on register allocation. So we will look at register allocation algorithms, a couple of them. The first one is very, very simple, given in our book Ahoseti Ullman, which is the standard Bible for compiler courses. Okay. So as we discussed earlier, we want to use those values in register which are going to be used soon, okay, or which are going to be used very frequently. So there are many different algorithms for that. So first we look at a very simple algorithm which looks at next use information to decide how to allocate a value in a register. Okay, and this algorithm works at basic block level. So I remember yesterday you had got some information about basic blocks from Professor Shrikant. So I hope everyone knows what a basic block is. Okay, it's a sequence of single entry and single exit instructions. Okay, so it's a sequence of instruction where you can enter only at the start and exit only at the end. There is no jump inside this block and there is no jump outside this block other than first and last statement. Okay, so how do we use next use information? So let's look at that. So we'll use it for register and temporary allocation. What we want is, if a variable is not used, we have to remove it from register. So suppose I have a statement x equal to y of z. Here x, y, z can be registers, can be variables. Okay, so this statement, it is using both y and z, and it is defining x, right? And note that x, y, z can be reused. I could have x equal to x of z also, or x equal to y of x. So it's not necessary that all three are distinct. So because we are looking at use, we have to look in the future. Okay, so that's why what we will do is we will go through the basic block in the reverse direction. We'll start at the last instruction, go towards the first. And I'm not sure if Professor Shrikant covered a few data flow analysis in which you must have done some backward analysis as well, live variable analysis. So did Professor Shrikant cover live variable analysis yesterday? Anyone? Yes or no? So which data flow analysis did he cover? Available expression, reaching definition, live variable, very busy expression? Someone has to speak up. Okay, so only reaching definition. So in reaching definition, you start from the top of a basic block, or you start from the top of the program and then go towards the end, right? Here we have to do in the reverse direction. And again, I think Professor Shrikant did it at the basic block level, the function level. What we are going to do at a basic block level. So that way our job is much simpler, because we only have to look at sequential statements, no branching. So what we will assume, and again, this is kind of not a very bad assumption, that all temporaries are dead on exit of the basic block, but user variables are still live at the exit. What this means, see, we don't have much control over user variables. Users are going to use variable anywhere in the function, in a program. Okay, so a given variable can be used anywhere in the program across different basic blocks. But temporaries are generally generated by compiler and they are consumed almost immediately. Okay, very rarely temporaries will go across basic blocks. So that's why it's not a very bad assumption that we'll assume temporaries have a short lifespan. So they are only used inside a basic block. On the other hand, user variables have long lifespan, so they can go across basic blocks. So this is a heuristic. Okay. So suppose we are scanning this basic block from bottom to top, and we reach a statement number I, which has this statement x equal to y of z. So what can I say about this instruction? Okay. So what happens? Any use of x below this instruction will be affected by the current definition of x, right? Because we are talking about sequential statements. We are talking about single line code. So any use of x below has to be coming from this definition, which means any other definition of x above is dead. On the other hand, for y and z, because we are using it, so this forms the next use. At least the current next use for any definition above. So this is something we want to store in our somewhere. Okay. And what is that somewhere? Where will we store it? So you know that compilers have symbol table. So you can create some extra space in symbol table. You can maintain extra space to keep this information. However, there is one more challenge, because this information changes at every line. Okay, so I-1 information can change. Maybe x becomes live again, or y becomes dead, and so on. So this information is dynamic in the sense every line has its own information. So symbol table will not suffice. Either you will have to put some kind of map which maps every line number to statement or information, or you will lose out, you will overwrite information. So in some sense, you have to also associate some information with the statement. Okay, you can have a separate data structure, or you can make it part of symbol table. That is implementation issue. But what we need is some information has to be stored along with the statement, and some information we will store in symbol table, because we are going through this in different statements. So we want to carry over some information. Okay. So with statement I, we will store information about x, y, z. And we will set x to not live and no next use in symbol table. So you can see that because x is getting redefined, its information, any definition above, is no longer live and it has no next use. Okay. And again, this ordering is important, because x can also, I could have x equal to x of z. So after we have done that, we have to set y and z to be live and next use as I in the symbol table. So once again, x will come back if it is x equal to x of z. So this ordering is important. This is what we do. So let's have an example. Okay, we'll only look at temporaries, but you can do the same about user variables as well. So we will do a backward scan. Whenever we see a statement, what we do, we process left-hand side variables and we process right-hand side variables or temporaries. Okay. So initially, all the temporaries are marked dead. All the user variables are marked live. So x, if I had been looking at that, it would have been still marked as live. Oh, sorry. So then I start processing line number 7. I'm ignoring user variable, but that has to be handled as well by the compiler. So we are using T6 here. Okay. So once we process left-hand side, we have to come to right-hand side. What we have to do with T6? We have to set its next use to line number 7. So initially, no temporary is live at line 7. and we have to say T6 is used in line number 7. Okay, and then only we move backwards. At line 6, I have to do multiple things. First, I have to set line 6 to hold information about T6 because that is what is getting defined here, and then we have to modify symbol table. So line number 6, it has the information. So this is a separate data structure that I will have to maintain. T6 has use in 7 and the variables T4, T5 are not live. So any temporary which is used in this line, I have to copy its information from the symbol table. And then I have to modify symbol table. So T6 is marked dead. T4 and T5 get their use set in line 6. Okay. Now I come to line T5. Once again, line 5 only defines T5. So T5 information gets copied. And then things get updated. So T5 becomes dead. T4 is still used. So any questions about it? Okay. Line 4, I need information about T4, T1, T3. And then I update symbol table. T4 is dead, T1, T3 are used. Now T3 and T2. So T3 is used, T2 is dead. But after this also, T3 becomes dead. And I keep doing this. Okay. So at the end of this whole pass, this is a single pass, you have complete information at each line. What are the variables which are defined? What is their next use? And so on. Okay. So in using this information, you can create what is called live ranges for the temporaries. So these are our statements 1 to 7. I know that T1 is defined in line 1. And if I just go back for T1, its use is in line 4. So T1 is being used from line 1 to line 4, even though it is not used in 2 and 3. So this is more like live interval. Okay. It has some holes where it is not really used, but we still want it to be marked as use. T2 is used, created in line 2 and it is used immediately in line 3. T3 is created in line 3 and immediately used in 4 and so on. So let's look at these things. So T1, then T2, then T3. What about T4? T4 starts in line 4 and goes all the way up to line 6. T5 starts in line 5, goes up to line 6. And then T6 starts at line 6 and ends at line 7. So it's live. Okay. So you can see that these lives I have drawn in a kind of a organized way, in a structured way. What I want to show is that there are variables or temporaries whose lives are overlapping. Okay, what that tells us? What does that information help us do? Any guesses? It's not very difficult to guess. So both are in use at the same time. Or so this is Prateek's answer, and Krishnan's answer is need a register to store all variables which are live. Yes, that is true, but that's means we want to use registers to store all live variables, but it tells us that T1 and T2 cannot use the same resource. They cannot use the same storage. Okay, T1 and T2 have to be given different storage. So what is happening currently? If I simply have an algorithm which maps a temporary to a register, then T1 will require 1 register, T2. So I will require 6 registers here in this program. But with this analysis, I am able to reduce number of registers to whatever the width here is. So at any given time, there are only 2 temporaries which require storage. Okay. So I can simply rewrite this program to reuse temporaries. So I can say T1, I have to start with T1. Then I need a T2, but then T3 need not be created again. I can reuse T2. So T3 can be renamed as T2. Then T1 can be T1 plus T2 because T4 can be renamed as T1. And T3 we have anyway renamed as T2 and so on. Okay. Something similar you did yesterday with the common sub-expression elimination using DAG or using other thing. Okay. But I want to say that it is similar in only in the case sense that you are renaming things, you are reusing the expressions there. Here we are not reusing the expression. Here we are reusing the storage space. Okay, so the expression computed by T2 at two different places is totally different. Okay, and in a way it goes against the previous philosophy of compilers from the previous stages, especially the optimization stage, where you do not want multiple temporaries, or sorry, same temporary to hold multiple different values. It makes analysis, it makes transformation very, very difficult. Okay, I remember someone was asking a question about why not use D equal to B instead of introducing a new temporary and reusing it multiple times. Okay, so when you will write those analysis, you will realize that if things are changing too much, if same variable is containing many different values at different points, analysis becomes difficult. Figuring out what is the current value becomes difficult, and that is why during target independent code optimization, okay, machine independent code optimization, you create temporaries on the go. You never kind of reuse temporaries. But here, now we want to reuse real resources. At that time, they are virtual resources. Now we have to map to real resources. So we want to reduce number of temporaries. So understand this conflicting requirements of different phases. The optimization phase, because it has to guarantee certain values in certain temporaries, it tries to create new temporary whenever a new value kind of gets generated. Okay. But now in code generation phase, we have to map these temporaries to physical resources which cannot be generated on the fly. So we want to reduce number of temporaries. Okay. So is this conflict clear to all? If we try to do such a thing in optimization phase, your analysis will become very, very complex. You will have to kind of keep track of multiple values at multiple points. There, each temporary is kind of assumed to hold a single value. Okay. So now you can see that this program can be written to use only 2 registers. However, we are lucky, I mean, this is kind of a cooked up program. In general, you won't be able to get such a nice fit everything into 2 or 3 registers or 2 or 3 temporaries. You will end up having few more temporaries than needed. Okay. And at the same time, currently we are only discussing temporaries. What about user variables? They are also there and they should also go into registers. So this simple allocation may not work for practical programs, but it still works at basic block level. So it helps us reduce temporary requirements. Okay. So let's look at a very simple code generator which will work on such 3 address code. So again, our simple code generator will go through individual statements, but then it will have some global view by remembering which operands are in registers and which are not. So it kind of keeps track of the values stored in registers and also what each register holds. So there are 2 kind of descriptors or maps it maintains. One is register descriptor. This keeps track of what is currently in each register. So you ask what is in R0, it gives you variable A. You ask what is in R5, it gives you temporary T5, like that. Then you have a kind of reverse map. It's an address descriptor. You ask where is A, it will give you register R0. You ask where is temporary T5, it will give you register R5 or memory location or whatever. So register descriptor is mapped from register to memory locations or values, and address descriptor is mapping from addresses to registers or other things. So it can be register or stack memory or even a set. Some values you will see may end up in more than one places. Okay. However, a single location will hold only a single value. So how do we go through? So any queries before we move on to the actual algorithm? So please ask question, because again, sometimes I feel like I am not audible, or if I am going very fast, you have to stop me. So initially it's cold, so I go slow, but then slowly I warm up. It is getting sunny, so I might start going very fast. Okay, no questions till now. And also tell me if all of you have covered this stuff, then I will skip on to the more complex register allocation. Okay. So, right. So again, we are only discussing x equal to y of z because that's that kind of encompasses other kind of instruction. So if it is just x equal to y, you ignore z part. Or if it is x equal to op y, that also. Okay. So what we need is a function GetRich, which will determine a location L where x must be stored. So we have this statement. Code generation has to determine where x gets stored. And as we saw earlier, operations, or as we discussed, means we did not really see it, as operations on registers are faster, we would typically want x to be in register, and we would like to remember it so that if later statement uses x, we need not issue an extra load instruction. We could reuse the register for where we have stored x. Okay, so that's where register descriptor and address descriptor help us. So now we would like x to be stored in a, usually we want it to be stored in a register. Okay, and we will assume a machine model where like we saw earlier, some kind of Intel-like machine model where one of the operands also holds the result. So when I say add R1 comma R2, it actually means R2 equal to R2 plus R1. So you are using second argument as first parameter to operand, as well as it will be used to hold the result. Okay, so second operand of the instruction will hold first operand of the code, 3 address code, as well as the result of the 3 address code. So it's slightly non-symmetric, but that's how many architectures are. And it is easy to change it to other architectures. Okay, so because we want first operand as well as the result to be in the same register, we will first check where y is. Okay, let's say y is stored in some location y prime. This is obtained from address descriptor. It could happen that y prime, there are more than one locations for y. So then we will prefer a y prime, which is a register. Okay, now this y prime may or may not be in our target L, which we want. Okay, so why this won't be in L, we will see again. Later we will see how to choose L. Okay, if y prime is already in L, then we are good. But if y prime is different from L, then we have to issue this instruction, move y prime to L. Okay, so because we want L to hold the first operand as well as the result. Next, you do same for Z. Okay, but for I think some line is missing. Okay, so I have kind of merged that. So second, you figure out what Z prime is, which is the descriptor, which is the location for Z. Okay, this Z prime, again, you will prefer a register. Okay, and you are issuing the operand. So note that once again, this will mean L equal to L of Z prime. In our 3 address code, we are already decided X value goes in L. As a result, we have moved Y value into L if it was already not there, and Z prime holds the value of Z. So this is really realizing that instruction X equal to Y of Z. So if L is a register, now note that we have changed the content of L. So we have to update this descriptor to indicate that it contains X. We have to remove X from all other register descriptors. And we also have to update register descriptors. Okay. So if Y and Z are not going to be used anymore, then we will, and they are still on registers, then we will change their register descriptors. Okay, we will free the register descriptor so that others can use it. Okay, so that's the idea. And we will have an example very soon. But before that, I have to describe how to get that L. So idea is clear, right? We try to find out a register for Y, and is it possible to reuse it for X or not somehow? If that is so, then good. Otherwise, we move value of Y to a register which can be used for X, and then we find out preferably a register for Z. If not, it can also be memory. And again, there are other restrictions. For example, some architecture like MIPS would force you to have register for both of these. Okay, in which case you have to force Z prime to be a register. If Z is not in a register, you have to introduce another instruction like move. Okay, so that's the idea. So GetRich, how do we decide what variable to use for X? So remember earlier, I have just mentioned that there exists a function GetRich. Okay, I did not tell you how to determine that. So now we'll look at that. So suppose Y is already in a register and Y is not going to be used. Okay, then you know that Y, this is current use is the last use of Y, and this register can be considered as free. So we will use that same register for X as well. So that way you are saving on one move instruction. Suppose either Y is not in a register or Y has some more usage. Okay, then you can pick up an empty register. Remember that you will have to issue a move instruction in this case. Now, suppose there is no empty register for X. Okay, you are unable to find all registers are in use. Then you check whether X has a next use or not. Okay, either that or your machine architecture requires that first the result has to be a register, or first operand has to be a register. Okay, then you will pick up some register using some heuristics. Again, this heuristics we have not defined, but looking at what is the maybe closest next use or farthest next use or things like that. Okay, you spill. This is called spilling. You move its content into M, and then you start using the register. So this is something which will introduce an extra instruction. And this instruction is quite costly because it's actually a move to a memory, not to another register. So that is why it is important to have sufficient empty registers available. That is why we want to clear Y and Z when they are not in use after the instruction. Okay. Suppose none of this exists, and assuming that X can be in memory location, you will use that memory location as Z. Okay. Assuming your architecture allows you to generate result in a memory location. So that's all. That is your GetRich. So this is a very, very simple allocation, register allocation based on the usage of a variable and based on certain machine specific constraints, and it works only at basic block level. Okay, so here is an example. So we have 4 statements. We want to create registers. We want to create instruction using registers, the minimum number of registers. So we have T1 equal to A minus B. So what we want to check is, initially there is nothing. I mean, this is where our program starts. So all registers are empty. So A is also sitting in a memory location, not in any register. So how do we work with this? So first thing, you have to move value of A into register. And then you have to generate the operation. So you are subtracting B from R0. Now, once this code is executed, you know that I mean, we are not executing the code, but we know that this will be executed, and as a result of which R0 will contain T1, and you also have to tell that T1 is in R0. So you will update both register descriptor as well as address descriptor. Okay. And now you will see that it helps us in the next statement or one statement later after that. Here we have to issue T2. So we move A to R1 because no register contains A1. T1, so we can reuse T1. Am I audible? Because my system says internet connection unstable. So are you with me? Okay. So third statement is the statement which will get most benefited, because both arguments are already in register, and secondly, the first argument has no use, so we can reuse its register. So we can simply issue add R1 R0, which means R0 plus R1, which means T1 plus T2. So as a result of this, R0 now contains T3, R1 still continues to hold T2. And you can see that the way things have worked out, again, we are kind of lucky, because fourth statement also need not do any extra work other than actual operation. As a result of fourth statement, R0 will contain value that is required for D. Okay. Now, if this is end of the program, finally you have to make sure the memory location of D stores value of D. Okay. If it is intermediate thing, again, depending on your compiler, you might avoid issuing a store instruction at this point. You will do it eventually when D gets printed or something like that. But you might avoid it. That is where reordering of commands come into picture. But here, this is end of the program, so we have to move the value into D. This is something you cannot avoid, assuming other basic blocks depend on it. Okay, so you can see that this register allocation works for a simple code for a basic block quite decently. Okay. However, in real program, we have to worry about multiple basic blocks, and we will come to that. So before that, just something to revise. Again, it was covered yesterday in lot more details, that the expression inside basic blocks. Okay, so you can use this DAG representation to reduce requirements of temporaries. Okay, you can do a lot of common sub expression elimination, which also in turn will give you reduction in the number of code. I would not say, it may not directly give you a reduction in number of temporaries, but it reduces the size of your code. Okay, and indirectly it might result in fewer temporaries being used. So here is the program and corresponding temporary, but since yesterday you have done it in lot more detail, so I won't go into too much details here. Just assume this is correct. Okay. So if I generate code without temporary, or if I just translate into storage without temporary, without DAG, it's one-to-one correspondence between the earlier statements and this one. So I just explicated few things like array dereference. But if I use DAG, I can delete lot of common expressions, like S4 is gone. Similarly, these two statements get combined into one, and similarly these two statements get combined into one. So in a way, I am able to save on certain locations. Okay. Now DAG, one of the issues is it will still look at these statements in order, and in some cases it may not be able to give you much benefit in reducing the number of temporaries required. So let's look at example here. Now, in fact, though I call it a DAG, it's really a tree. and therefore you are not really going to get any advantage of common expressions. Okay, so I have few statements which really do not have any sharing. I mean, there's no code reuse or more expression reuse. Okay, so I end up getting a tree, and it should be quite obvious that for such a tree, you are not going to get any benefit from using a tag. Okay, so which means when you generate code for such a tree, it does not matter whether you use tag to optimize it or not. So let's assume we have this code and we want to generate generate final code using only 2 registers. Okay, I think I should have called generated code assuming only 2 registers. So here is the code. So we move A to R0, then we add B to it. Then we are doing register optimization. So I'm not moving anything into, so T1 already is there in R0. Similarly, T2 is already there in R1. Now we have only 2 registers available. So when I have to compute T3, T1 has a use below, so I cannot free its register. T2 I can free it, but then I still have to store E somewhere. Okay, so T2 is used currently and I have to store E, so I need a third register, but my architecture has only 2 registers available, so which means I have to move R0 into memory. I have to spill T1 into a memory location. I have to compute T3, and then I have to load this T1 back. Only then I can perform the last operation. Okay, so try to generate code for it with just 2 registers. You will find that it is impossible. Okay, without moving things to memory location. Okay, but then what is happening really? If there were 3 registers, I need not use these 2 instructions. Okay, so what it shows us that sometimes it will happen that the registers available are not sufficient to generate code even after you have done optimizations like DAG to remove common sub-expression elimination. You have figured out live ranges to see where all temporaries are getting generated and used and so on. Still you will end up spilling your code. Okay. However, if we rearrange the order of code, there is still a possibility of avoiding this spill to memory. Okay, so what is the problem here? Problem is T1 is getting computed very early. These 2 statements do not use T1 at all. Okay, but T1 is computed and stored, and that register kind of gets blocked. So what if we move it here? Computation of T1. We cannot do it in an unrestricted fashion. Okay, in this program we can do it because T2 and T3 do not use T1. So I can as well bring T1 down. So we rearrange the code. So we first compute T2, we then compute T3, then we compute T1, and if we do x equal to T1 minus T3, and it will give you a code which works with just 2 registers. There are no spilling. So you can see there are 3 plus 3 plus 4, 10 instructions here, but only 8 instructions here. Okay. The code is correct. Once again, you can go through it at your leisure time. But the idea here is first instruction used 1 register, second instruction used 2 registers, but immediately after the instruction is over, it could free this register T2. T2 is no longer required. So it does not need to be stored, it does not need to remain in the register. And therefore, I could reuse register allocated for T2 to compute T1 and then use those 2 registers to compute X. Okay, so this is the intuition. Right? So by rearranging the code, we are able to improve the efficiency. We are able to do much better register allocation. And in particular, we are avoiding this register spilling and register reloading. Okay. So how do we do this rearranging? So within a basic block, there are There is a very powerful algorithm called Aho-Johnson algorithm, which does all this. Okay, it really looks at the definition of a temporary, it looks at how it is used, and then it is able to move things around. Other thing is you can also do some kind of data flow analysis to figure out definitions and their usages, and bring definition close to usages as far as possible without violating other dependencies and so on. So you can do dependence analysis, I would say, rather than reaching definition analysis. So there are complex analysis which can do that, but at basic block level, you can do it using what is called an Aho-Johnson algorithm, which is in fact used in many of the production compilers. We are not going to cover that, but it can be done. That's the idea. So any question? So this also tells you that when you are writing your code, I mean, if you don't want your compiler to have too much trouble, make sure the values you compute them as close to their use as possible. Okay, this will reduce what is called register pressure. So value gets computed and then it gets consumed and resources become free. Okay, now it's not 100% possible at high level programming level, because compiler will introduce temporaries and so on, but compilers will also sometimes try to introduce temporaries and consume them immediately. Okay, that is the idea. And you have Professor Srikanth also talked about few code movement optimizations, code motion optimizations. They also try to do things like this, move definitions and usage close together, so that it reduces the pressure. Okay, and this is also a challenge with the certain code movement optimization. Like you talked about loop invariant code motion. In general, loop invariant code motion will give you benefits. Okay, I mean, almost all in all cases that optimization is going to give you benefit, but you can come up with a pathetic case using these ideas, that you move definition very far away from the use and have a loop which only executes once. Okay, so that way you can fool your compiler into generating a code which is suboptimal. Okay, and it's really impossible to figure out all possible such cases using static analysis. Right, so no questions. I hope I made sense. I gave you some idea about optimizations, register optimizations. Okay, so yeah. So next half an hour, I will describe a very, very popular register allocation algorithm. And these slides are by Keith Shavars of Stanford. So I have not created these slides, rest of the slides. Okay. So what we want to do again, find out how to assign variables to finitely many registers. And then as we saw, there will be cases when it can't be done. So what to do there and how to do it in the most effective way. Okay, so some definitions, and again these are very similar to the definitions you saw yesterday as well as the concepts we covered earlier. We say that a variable is live at a program point if its value may be read later before it is written again. Okay, so at a given program point P, I will say a variable V is live if in some execution of the program before exit and before last statement, I am going to read V. Okay, there can be multiple paths, but as long as I am doing it on one path, that is good enough. Okay, now we also have to make sure that the value used here is the value we are seeing here. So there should not be any assignment to the values in between. Okay, so that's why it says if its value may be read later before it is written. So I can have a writing here, that's okay, allowed after it is read. So in a way, if I stand here and look down on this path, I should see a V being read. This writing blocks my vision. Okay, so I should be able to see that. So just like you did the reaching definition, you can do this using liveness analysis. Okay. So we can define what is called a live range for a variable. So this is the set of program points where variable is live. So you go at each program point, look down, collect all the variables that are live, and you get live range for different variables. And now these live ranges, as we saw, can have holes. I mean, I use a variable at line number 1 and line number 22. So maybe it is not used at line 2, line 3, line 4. So live interval is the smallest subrange of the IR code. So the first statement where it is used and the last statement where it is used. All the statements in between, which so it contains all live ranges of the variable. So note that this is a property of IR code. IR code is a straight line thing. Okay. CFG has branches. So we want to talk about a starting line and the last line, which encompasses all accesses to a variable. So as you can guess, live interval, because it is encompassing all live ranges, you have fewer of them and it is easy to work with. But then it is also imprecise. I am also including many points where a variable or temporary is not used. Okay, so I will have over approximations here. So my program may end up being little less optimized if I use live interval. But then because we also want our code generator to be fast enough, it's better to work with live interval for most algorithms. So here is a small code in a pseudocode, assembly like pseudocode. Okay. So on the right hand side is the control flow graph for them. So we can compute live variables using a backward analysis. And this idea is very same as we used in next use. Every assignment will kind of make right hand side live. And so it will first kill left hand side and it will then make all the things on the right hand side as live. So we'll assume this last variable. I don't know what happens below this, but let's assume it is live because it has just been defined. So hopefully someone is using that. But that depending on your initialization, it could be different as well. Before this assignment, clearly I cannot use G before defining, right? So by our definition of live variable, G cannot be live here. No use of G below can be there, which uses previous value of G. G is getting redefined immediately after this point. So G can no longer be live. On the other end, I see a use of D just below me. So D becomes live. What about this point? If I look down, I can see D being used, nothing else. If I am here at this point, if I look down, I can see D being used, but nothing else. What about this point? If I look down from this point, I can see E being used, I can see F being used. However, I do not see any other variable being used. Even though D is being used, my vision is blocked because of this assignment to D. Okay, I cannot see D being used below because this thing blocks my view. Okay, and same thing I will do for all the statements. And I need one path, any one path on which I should be able to see the usage. So this is a very informal way of describing live variable analysis. So let's do that quickly. So EF, BEF, BEF, BCE, BCE, and ABCD. So just to quickly check, why is ABCD live here? I can see one use of A here. I can see one use of D here. If I go down, I can see a use of C. I can see a B. And there is no definition of B or C or A or D before their use. So all four ABCD are live. But if I am at this point, I do not see any use of A anywhere on any path. Okay, so A is no longer live. Same about D. Even though I have a use, it is getting blocked due to these definitions. Okay. So if I want to find live ranges and live intervals, so A is only live at start. B is live here, here. So basically here, here, up to this point, I think. Then C, D. So D is live in patches. Okay, it's live for some time here, then it is live for some time here, it is live for some time here, but not at other places. Okay, so this is live range of D. If we want to work with live interval, this will be live interval of D. Then we have E is live interval, F, and finally G. And please note that again, it's not very clear whether G is useful or not, but we are assuming someone is going to use G at the bottom. That's why I am marking it as live. Okay, it's in the rest of the program which we don't have access right now. So if this is clear, then we can go to register allocation. Okay, and you can see that once again, like we did earlier, at this point, if I have to put all the values, live values in register, I need at least 4 registers. Okay. So in a way, if I put all these live intervals together, and if my number of registers is more than this width, where all the things are live, then my register allocation task becomes trivial. I can put everything in a unique register. Now challenge comes, suppose I have 3 registers or 2 registers. Okay, so then there is a challenge. And for our, simple programs, we are working with 2-3 registers, but generally there are numbers is around, in kind of tens of few tens. So MIPS has some 32 register. I don't recall what Intel has nowadays, but earlier it used to have, I think, 8 registers. Okay, but it cannot be hundreds of registers. So yeah, this is what we want to say. What we infer from all these variables being live at this point, we infer that we cannot allocate them to same registers or same storage location. Okay, need not be register. They have to get their own storage location. Okay, so how do we capture it? So basically, we can capture this information. Again, one way is go through all the statements and capture this, but that's not a very useful way. It will be very, very time consuming. It's not going to be efficient. So we can capture it by using some kind of conflict graph. So whenever I see that A and B are used together, I will create an edge between them. Okay, so I create node for individual variables. And here I am including temporaries. I mean, I'm not distinguishing between variables and temporaries, right? So I am creating node corresponding to each of the value that is of interest. And then I am putting an edge between them. This edge is a edge describing a conflict. It says, if I am connected to you, then both of us are going to participate in this program at the same time. So it is better that you get your own space, I will get my own space. Okay, so this is not an edge of kind of friendship, this is edge of conflict. So we added these edges. So A is, A, B, C, D all are in conflict with each other. Then B, C, and E are also in conflict with each other. And then B, E, and F are conflict with each other. And I think that's all. E and F are conflict that we have already captured. That's all. And G is never conflict with others. D is already we have captured. It's okay. So this is our conflict graph. Now suppose we have 4 registers to allocate. So in this case, this kind of trivial because we saw only 4 variables at the most conflict with each other. We give them 4 different registers, and this color kind of show which register goes to whom. And G does not conflict, so it can take any register. E can take any register. F conflicts with the blue and yellow, so it can get either pink or gray. Okay, so I have choice for F. Okay, so intuitively we can do this. Okay. Any questions about anything until this point? And this is very important concept to grasp. That because I have more registers or at least as many registers as there are conflicts, my register allocation is very, very easy, trivial. Okay. I cannot give same color to A or B or B or C or A or D, because then it will be saying use yellow for both A as well as D, which is kind of conflicting. So I have to give them different registers or different colors. So this graph has a name called register inference graph, and it is an undirected graph because it does not matter whether I conflict with you or you conflict with me. It's the same. Each node is a variable. There is an edge. Okay, so let me just come back to a question. We have performed register allocation by assigning each variable a different register from all its. Okay, so no, somebody says why A, D disconnected in graph. No, they are not disconnected. See, A and D are connected. A and G are disconnected. I have no point where A and G are used together. Okay, Sayam, am I right or is something I missed?
I think you just drew the line, right, between AD. It wasn't there before, right? The edge.
No, I did not get AD. What are you saying?
Yeah, so this is a new edge, right? Like it wasn't drawn before, right?
No, it was there. It is always there. Let me just see. This is always there. The first thing I did was connected A, B, C, D all with each other. Because at starting point, they are all useful.
Yes, but there is no edge between AD here. A and D.
No, here is A, here is D. I have an edge. Where it is not there, I can't get it.
So, like, I don't know, like, maybe I'm getting confused, but I don't see any edge between A and D here.
No, what do you mean by here? Do you mean control flow graph?
No, like, since they are A, B, C, D, right? So, between A, B, C, D, if we want to connect them all, then there would be a direct edge from A to D, right?
What about this? Are you okay? So someone else, are you seeing an edge where I am drawing my line? I have drawn it halfway.
Yes, now you are drawing it. I'm asking, like, it's not there in the slides, right?
It is there. It is there. There's a black line below it. Maybe so. That's why I'm asking others. Can you see that black line?
Yes, sir.
Oh, so probably I mean rendering might be bad. So in fact, there is this line present. I'm just drawing on top of it. Okay, this line is present in the graph. I don't know why it is happening. Let me just.
Sir, it might be that.
So can you see now? I have moved away from slideshow mode.
Oh yes, now I can see it. I guess it was just too light to see them.
I think probably some kind of what do you say, display issue, whatever system you are using. Okay, so it is there. In fact, it is there in all the graphs.
Yeah, okay, that's
it's not getting entered in your system. Yes. Sorry for that. Yeah, that is a very unique kind of problem. Okay, and then now you can understand my confusion. That I was seeing it right there, and you are saying it is not there. So please, in fact, so it is there. So that's all I can say right now. Okay, so this line is there. All right. So let me quickly go to it. So basically, what we have to do now is perform register allocation such that a node gets a register which is distinct from all its neighbors, and neighbors are defined by nodes which are connected through an edge. Okay, very simple, right? It's easy to describe, it's easy to create such a graph, not very difficult. Single pass after liveness analysis will give you this graph. So what is the catch? This problem is same as what is called graph coloring. It's a very well-known problem in mathematics or computer science, and it's an NP hard. I hope you all know. If you are not aware of NP hard, just you don't have to worry about it. It does not have an efficient solution. If you have a solution, you can verify it quickly, but you cannot get a solution very quickly. Okay, so there is no polynomial time algorithm for this problem. So as you can guess, if your compiler starts using non-polynomial time algorithm, then it might happen that that 5-line program can take 20 hours to compile. Okay. So we want to have some kind of an approximation or heuristic. So now you will say, oh, I am saying not or even good approximation, but then we are saying we will have an approximation or heuristic. So in this complexity theory, when we say an algorithm has an approximation, then there have to be certain guarantees that its cost will be at least double, or it will be at least 2 times or 3 times worse. Some kind of bound we have to give. For this problem, we cannot give any bound. Okay, but then for compiler, I mean, it's like, yes, the code generated will not be best possible code, but it will still be correct. So we really don't worry about bounding a bounded approximation in certain sense with guarantees. We just say, okay, we will try our best. Whatever happens, happens. Okay. And secondly, our approximation will be good enough for graphs that arise in practice. Okay. Very rarely, or you will have to spend some effort to come up with a graph that will not work. Sumit, I think you're muting you. Okay. So the one cache to one catch, but I think most of you might already be knowing about it. So if you can figure out where to assign registers to any arbitrary RIG, then you have proven P equal to NP, and you will get 100,000, I think, or $1 million check. Okay. So there is an algorithm to the graph that we have created. So what you can do is, you can start with a node which has fewer than k edges. Okay. Now think about this graph. Assume, just for the sake of it, you can k color the graph. Okay. Then you can show that even if you delete this node which has fewer than k edges, and suppose you can k color the remaining graph. So you have one less node, you have few less edges because you have deleted one node and its edges. And suppose you can k color that graph, then you can bring back the node. So there is this node, there is some rest of the graph. This node is connected to less than k edges. Okay. So if I could k color this part of the graph, clearly I can always color this extra node which I had ignored earlier, because whatever it is connected to, there are less than k neighbors. So at least one color will not be there on any neighbor, so I can use it. Okay, so this is a recursive algorithm. You delete a node, you recursively color rest of the graph, you add this node back, you add all the edges, and then you color the correct this node. Okay, so because with fewer than k neighbors, some color must be left over. So anyone having any questions about this? So the algorithm is find a node with fewer than k outgoing edges, remove it. When we say remove it, remove all the edges as well. And again, when we say remove it, don't actually throw it away. Somehow mark it that it is not part of the graph, because you have to restore it back. You recursively color rest of the graph. Now you restore the node and you assign it one of the colors which is not there on any neighbor. Okay. So looks like we have solved graph coloring problem. So what is the catch here? What is the missing here? So where did we missed something? Anyone? Right. I mean, not just greater than equal to, see, as long as there is one node with less than k color, we can continue. Okay. Problem is, what if none of the nodes have less than k edges? Okay. So that way you can see that this algorithm is not able to handle those graphs. And therefore we have not really solved graph coloring problem. So that is the case where we have to be a little bit more innovative. So I will quickly go over this. I mean, this is not okay, but it's not so non-trivial. So just show you how it will work when you have sufficient number of colors. So here there is no edge with no node with more than 3 neighbors, or at most 4 neighbors. Let me see. Yeah, at most 4 neighbors. So here we have 4 registers. So we will find out nodes which have less than equal to 3 neighbors. Okay, less than k. So basically less than equal to k minus 1. So C is one such node, and it does not matter which node you pick up, as long as it has less than k nodes. So I remove it from the graph. Now can I find a node which has less than? Yes, I can find B, I can find E. So B, I remove it, I select D. I could have selected E, but it does not matter. And I keep doing this. Okay. So note that originally B had 4 edges, but the moment I deleted C, I could find B as having less than equal to 3 edges. So that's how it works. So in this graph, we are lucky, we are not stuck. So now we can start coloring because recursion has reached its bottom, which means you can always color an empty graph. Okay, so empty graph has been colored. You can, this is the base case. Now you add F back, you assign it any color you want. We will typically go from left to right in register allocation. So now when you bring back G, you cannot assign yellow color to it because it's already consumed to for one of the neighbor. So you'll have to give it blue. Then you bring back A. You have to remember the order in which you remove. You have to add in the same order, in the reverse order, and so on. Okay, so I think that is good enough. So this was a what do you say, lucky case, but we are unlucky when we can't find a node with fewer than k neighbors. So then we have to choose and remove an arbitrary node. So this is a heuristic. At the same time, we will mark it. Okay, because it's not a regular node anymore. It is a node where we have to do something extra. Now, once again, just because it is troublesome, it might still be a case that at the end you are able to find a color to it. Why that will happen? It could happen that there is a node which has 4 neighbors. Okay, but I mean, you are lucky enough that all 4 neighbors got same color, or they could be colored in 3 colors. Okay, so just because you could not find a node with fewer than k neighbors does not mean you are necessarily, you cannot necessarily color it. Okay, you can still be lucky. When we come back, you might find that, oh, all neighbors have same color. So then you can give it another color. Okay. However, I mean, these are all heuristics, so it may or may not work. It may work for one possible choice, it may not work for other possible choice, and so on. So we'll see those examples quickly. I am kind of running out of time, but I will show those things. Okay. So when adding, if you can find a color, you are lucky, then give it a color. Otherwise, you have really reached a pathological case, then you have to spill that node. So this is what Chetin's algorithm will do if it cannot find a color for the node, which means there is a requirement that you have to spill that register. So all those details I have not included here, but we'll just go through this added complexity. Now we have a case where we have just 3 registers and we have to color the graph using 3 registers. But as we will progress, this is the real graph what we had earlier. So G can be always picked up, F can be picked up after that, E can be picked up after that. But now you are in trouble because you have all nodes having 3 neighbors. Okay, so you don't know which one to pick up, so you can randomly pick up D and you mark it that this is troublesome. Okay, so you have to remember this. Now rest of the graph, again, we no longer have to worry about D because somehow we will take care of it. So A, B, C can be handled as if they are nice nodes. So you need not mark them anymore. Okay. While coming back, you color A, then you color B, color C. At this point, you can clearly see that D cannot be assigned a color. Okay, so this is we are just giving it a random and some kind of marking that D cannot be colored in this graph. It has to be spilled. It can be brought in temporary into a register, but in that case, you will have to spill it immediately. Okay, and the rest of the graph can be colored. Right. So this is the case where we had we were stuck. We removed the node and we were able to color the rest of the graph. Okay. Now there are few additions on top of Chetin's which we are not going to describe. But why did we have to? I mean, why did we have this problem? Okay. In this case, the problem is occurring because of this D, which has a very long live range or live interval. Okay, even though it is not really used for a long time. So this problem is happening because we are reusing it. Okay, so some algorithms can decide and introduce new temporaries in the program. So you can rewrite this code to use D prime instead of D. And now you have split the live ranges or live interval. And then again, it may not always work, but in this case, it will work. You have a graph which can be colored in 3 colors. Okay, so because D will no longer, so this can be colored, I think. Yeah. So, but I wanted to go with another example quickly. Time is already over, where the choice of node will matter. Okay, so the reason graph coloring is complex because choice matters. So here is a different graph, not related to the program we have seen, completely arbitrary graph. So we cannot find any node which has less than 3 neighbors. So all nodes have either 3 or 4 neighbors. So we have to pick up a node to split, to spill. We still have challenge because still there is no node less than 3 neighbors. So another node selected to spill. Now we are in the nice subgraph. So we can pick things one after the other. Okay. And we can start coloring them back. So D gets color yellow, F gets color yellow, E gets color blue, B gets color blue, C gets. So now look at this. C is a problematic node, but we are lucky enough because all its neighbors have been colored using just 2 colors, though there are 4 neighbors. So C could get the 3rd color. And same thing about A. Okay. So there are few heuristics about choosing the nodes as well as choosing the color. On the other hand, while choosing, I mean, here I'm not changing the order of choosing the node. If I change the color choice, now you will see that I am not able to color C anymore. Okay. Why? Because C has 3 different neighbors with 3 different colors. So there is no choice remaining. So I have to mark it to be spilled. Same about A. It has to be spilled. Okay. So you can see that a small change in algorithm or a small change in the way we select colors can result in a graph which can be colored versus which cannot be colored. Okay. So few advantages. So in general, Chetin's algorithm works very well, and there are other improvements suggested by Briggs and others. Okay, and there are certain suggestions at the control flow graph level, like splitting the variables or creating new variables and so on. So you can see that that is what makes your compiler's job very, very tricky. Some parts want more and more variables for optimal code. Some other part want number of variables to be less. In case of register allocation, it is not very clear. Generally, we thought that, oh, having fewer temporaries will work better. But we saw a case where introducing a new temporary or new variable will resulted into a better register allocation. So in register allocation, it's actually very, very complex to figure out what will work. Okay. So Chetin's disadvantage is, I mean, the core algorithm is kind of using NP hard, but I don't think that's a big disadvantage in compiler. There are many problems we are not even decidable. Okay, but we still use approximations. And it is possible, again, we saw that depending on our heuristic, we might end up doing very bad assignments. Okay. But then it is correct. I'm not going to go into that. You can quickly see that you will never assign same register to two variables at the same time. You can do a lot of improvements. And finally, there are other algorithms as well. Unfortunately, I have not read about it, so I could not cover them. But if you look at the complete slides by Professor Keith, they have these linear scan algorithm as well. So I have skipped over those slides. So this is used for JIT compilers for kind of on-the-fly register allocation, and it is a linear scan. Okay, so it is a greedy algorithm. Again, it's not guaranteed to produce best possible assignment of registers, but then it works well in practice. So we will stop our first session here. Any questions? Yes.
Sir?
Yes, Gaurav.
Yes, sir. I have a question. Where you said that one variable should not be assigned to more than one register, right?
One variable should not be assigned. No, one register should not contain more than one variable at a time.
Oh, okay. So then I have a question regarding. Can you go?
That was my mistake.
Yeah. Okay.
Yeah. I might have said it in the reverse way. Yeah, that is possible. So what we want, no two variables are assigned the same register at a given point.
Okay. So, sir, can you go to the previous slide before that rearranging of the statements?
Oh, the very early slide. Okay.
Yes.
Go back. The assembly code where we did the rearrangement, right?
Yes, sir.
Yes, this one.
Yeah. Before this.
Before this.
Yes, sir. Before this also. 3-4 slides before.
Which one?
Okay. More before.
So what was there on that slide? Can you?
Yeah, so I just want to ask, as we are rearranging these ASTs, right? 3 address codes. Can we do the same on this assembly code? Because at the time, in one example, I saw that it was move some variable A into R0. Then this R0 was modified, and then again A was loaded into R1. So can we rearrange it here such that after moving A to R0, we move R0 to R1 also? So because transferring between registers will be faster. Yeah, here I think this is the example.
Okay, yeah. So this one, A to R0, A to R1.
Yeah, so instead move the A to R1 to before subtraction and
okay, so not only you are saying you will move this instruction, you will also do some optimization that R1, instead of saying move A to R0, you will say move R0 to R1. So basically you will create 2 copies of A, because you know there are multiple different usages. Okay. I am not aware of any such optimization being there, but no one stops. You can always come up with your own optimization. I am not aware of an optimization where you kind of proactively copy a value into more than one registers by looking at next usage and so on. See, you'll have to think about how will you analyze such a situation.
Yes.
How will you figure out whether what is the need? Okay. On the other hand, I don't think in this course we are going to talk about p-pole optimizations. So p-pole optimizations, many of them are informal kind of optimizations as well, because you are working on 2, 3 instructions or 4 instructions at a time. Maybe in such case you will end up having a p-pole which is like this. Okay. And in this p-pole, you say, oh, there are 2, move A to R0 and move A to R1 quite close to each other. There are no jumps in between. There are no jumps out and so on. So maybe, yes, you might end up having a p-pole optimization like this. I can think about having a p-pole optimization but I'm not aware of anyone doing it as of now.
Okay, thank you, sir.
Because these 4 instructions, you can do a lot of optimizations which are not even which we may not even have a very deep theoretical background. Okay, people optimization, you do very informal optimizations as well. So you found out, but yeah, they have to be correct. And when I say informal, I'm not saying do something randomly. Okay. And there is a research work which I am aware of, which does something quite unexpected. They generate assemblies, many different assembly programs, and they do reordering. I cannot recall exactly how they do it. I think Shubhajit can also remember. Rahul Sharma, right? Alex Aikin, where they reorder assembly code and then verify that the reordered assembly code is equivalent to the original assembly code, and then come up with the best possible assembly there. Okay, so it's quite complex code. I mean that optimization. But it's not like a data flow optimization where you do a lot of analysis to figure out what moves where. In some sense, they do random movements, but then verify that movement against using some kind of verifier.
Correctness.
Right. So to guarantee correctness, they replace one instruction by other. They will delete some instruction, introduce some complex instructions, and so they do a lot of complex things which are verified for correctness later. While doing it, they don't care about correctness.
Thank you, sir.
Okay. So yes, then let's take a break for tea or coffee.
Sir, Amey sir?
Yes.
Sir, was it on super optimization? Like, I mean, the idea which you were saying, like they were
This
generating.
Rahul's work. Yes.
Okay. Yes, sir. Thank you, sir.
Thanks, Amey. Thanks for a wonderful session.